Usually when we talk about a scientific measurement or a medical diagnosis, there is this expectation of absolute precision. Like you break your arm, the x-ray shows that jagged white line, and the doctor just points at it. It is visible, it is categorized, and it fits into a neat little box.
Right, it's completely straightforward.
Exactly. But step into the world of agriculture and natural biology, and suddenly that clinical x-ray machine is, well, it's useless. We're looking at a landscape that is, both literally and figuratively, incredibly muddy. So, welcome to today's deep dive, where we are wading straight into all that complexity.
Yeah, it really is the ultimate unpredictable environment. I mean, a farm field involves soil mechanics, atmospheric pressure, solar radiation, genetics, and erratic weather patterns. And they were all interacting simultaneously. Trying to map that out mathematically is, notoriously difficult.
Which brings us to the core puzzle we are unpacking for you today. Imagine you have a specific seed, and you have a finite, predetermined amount of water. How can you mathematically predict the exact amount of food that seed is going to produce, say, 4 months later?
It sounds impossible, right?
It really does. But to figure this out, we are looking at a highly informative lecture from AGPS 301, Irrigation Design and Management. Specifically, we are exploring the introduction to a tool called the AquaCrop model. And our mission today is to extract the mechanics of how scientists take the chaotic reality of a farm and translate it into a precise simulation, all to ensure global food security.
And this wasn't like an overnight thing. The Food and Agricultural Organization, the FAO, they actually spent 30 years collecting data to build this model. 30 years of just trying to understand how crop growth fundamentally relates to water availability.
Wow, 30 years.
Yeah, it is a massive undertaking. The goal was to simulate the attainable yield of herbaceous crops. So that means your non-woody, fast-growing food staples like wheat, maize, soybeans. And they wanted to simulate that yield as a direct function of how much water those crops actually consume.
Okay, let's unpack this. Because people use this for high-stakes decision-making. The lecture notes list its applications ranging from, like, local irrigation management to massive regional project planning and even climate scenario simulations.
Exactly. It is used on a really broad scale.
But the detail that stands out most in the source material is the foundational philosophy behind it. AquaCrop is deliberately designed to balance 3 competing ideals: simplicity, robustness, and accuracy. Now, reading that brings to mind a complex city building or farming simulator video game.
Oh, sure, like SimCity or Stardew Valley.
Right. You manage resources, you tweak variables, and you watch a virtual world react. But obviously with AquaCrop, the real-world stakes are immense. People's lives literally depend on these yield predictions.
They really do.
So, if nature is famously complex and chaotic, balancing simplicity with accuracy feels like an impossible contradiction. You would assume maximum accuracy requires maximum complexity, wouldn't you?
You would, but it is actually the central tension in all ecological modeling. If you add too many variables, the model becomes so complex that a single bad data point ruins the entire simulation. But if you make it too simple, it just stops reflecting reality.
So how did the FAO solve that?
Well, they solved this by making the model fundamentally water-driven. Instead of trying to mathematically simulate every single cellular process or nutrient exchange, they focus relentlessly on a single primary driver. And that driver is the water being consumptively used.
Ah, so they basically stripped away all the peripheral noise to track the most vital currency.
Exactly. That singular focus is what makes it robust. But finding a way to actually measure and define that water currency accurately, well, that took decades of refinement.
And here is where it gets really interesting. Because the sources detail the evolution from an older methodology, specifically outlining the approach from an older FAO irrigation and drainage paper, number 33, the old conceptual approach linked the final crop yield directly to a metric called total evapotranspiration.
Right, we should probably break down evapotranspiration because it is essentially the engine of this entire discussion. It is actually 2 distinct physical processes happening simultaneously out in the field.
Okay, what is the first one?
First, you have evaporation. That is, liquid water converting to vapor and leaving the physical surface. Think of the sun baking the moisture out of the bare dirt or drying off wet leaves after a rainstorm.
Got it. And the second part?
Second, you have transpiration.
Transpiration being the moisture actively moving through the biological system, right? Like the plant pulls water from the soil, moves it up through the stems, and vaporizes it out through the microscopic pores in its leaves.
Yes, exactly. It is the plant breathing and sweating to cool itself and pull up nutrients. In the older models, They just lumped those two processes together into one massive variable, which was total evapotranspiration.
Oh, so they didn't distinguish between the two at all.
No, they didn't. They looked at all the water leaving the field and used a generalized proportionality factor to guess how much the yield would drop if that total water loss was reduced.
Okay, so trying to calculate crop yield using total evapotranspiration feels like trying to calculate a car's fuel efficiency by measuring both the gas burned by the engine and the gas you accidentally spilled on the driveway while filling the tank. The older models were essentially measuring spilled gas.
That is a perfect analogy. The spilled gas concept maps perfectly here. Think about when that spill is the absolute worst.
Probably early on.
Exactly. Early in a growing season, the crop seedlings are tiny. The canopy is virtually non-existent, meaning you have vast stretches of bare, exposed dirt between the rows.
And the sun is just beating down directly on the topsoil.
Right. And if you irrigate that field, a massive amount of that water is going to evaporate straight from the soil into the atmosphere. That is the soil evaporation.
The spilled gas.
Exactly. That water never enters the plant's root system. It performs absolutely no biological work. It does not help create biomass.
So AquaCrop's major innovation was blowing that old equation apart. It explicitly separates the total water loss into those two distinct components, the wasted soil evaporation and the highly productive crop transpiration.
Yes. And by doing that, the math completely strips out the confounding noise of the non-productive water use.
So it only looks at the fuel actually burning inside the engine. The new equation calculates the plant's biomass strictly as the product of its baseline water productivity multiplied by the cumulative crop transpiration, and nothing else.
That is it. And then, to get the final edible yield, you just multiply that total biological mass by the harvest index.
The harvest index being the proportion of that total plant matter that is actually useful, right? Like if you are growing wheat, you don't eat the stems or the roots, you only eat the grain. So the harvest index isolates the grain.
Right, exactly.
The sources also note that to make this universally applicable, the model normalizes that transpiration using something called reference evapotranspiration, which, I'm not going to lie, sounds incredibly dense. I am assuming this is how they account for the fact that a plant sweating in an arid desert is under a lot more atmospheric demand than a plant sweating in a humid greenhouse.
That is exactly what it does. Reference evapotranspiration is essentially a baseline metric of atmospheric thirst. It is a standardized measurement of how much water a well-watered field of grass would lose under the exact same weather conditions.
Okay, that makes sense. So it gives you a baseline to compare against.
Exactly. And by normalizing the crop's transpiration against that baseline, the mathematical relationship between water use and biomass becomes remarkably stable. Whether you are running the simulation for a farm in arid sub-Saharan Africa or a damp valley in northern Europe.
So we have isolated the specific water we care about, the transpiration, and we know how to standardize it. But nature isn't a static snapshot. A farm is a highly dynamic environment. So how often does this model actually have to measure that atmospheric thirst to stay accurate?
Well, older models often ran massive end-of-season calculations. They just looked at the total water used over the year and the final yield, taking a really macro view. But AquaCrop discards that approach entirely. It calculates water use, growth, and production in daily steps.
Moving to a daily step makes a lot of logical sense. I mean, checking an annual calculation is like checking your bank account balance once a year on December 31st. It might show that you were bankrupt, but it doesn't tell you how it happened. A daily check catches a temporary cash flow crisis on a random Tuesday in March.
Yes, and if we connect this to the bigger picture, plants experience environmental trauma very acutely. A severe, localized drought right in the middle of the growing season, specifically during a critical phase like pollination, can completely devastate the final grain yield, even if the rest of the year was perfectly watered.
Right, because an annual calculation just glosses over that acute trauma. The daily step captures the physiological reality of the plant suffering on that specific Tuesday.
Precisely. And this daily accounting happens within an overarching structure that the lecture calls the Soil Plant Atmosphere Continuum, or SPAC.
SPAC. Which sounds like deep sci-fi, but it is really just a way of mapping the ecosystem, right?
Yeah, it just divides the physical world into interconnected submodels, creating a holistic ledger for the water to move through.
Let's translate those submodels, starting with the soil-water balance. Instead of reading out the complex algebraic equation the lecture provides, let's just look at the mechanics. The soil is essentially our bank account. The model tracks the deposits, which are the precipitation falling from the sky, and the human irrigation pumped onto the field.
Right, and then it tracks the withdrawals and losses. You have
Yeah.
the evapotranspiration pulling water up into the air, but you also lose water downward and outward. Gravity is always acting on the system.
So if the soil becomes saturated past its holding capacity, you get deep percolation. That is water sinking so far down into the earth that the plant's roots can no longer reach it.
Yes, exactly.
And if the rain comes down faster than the topsoil can absorb it, you get surface runoff. The water just washes away over the top. Though the source does mention that in a highly optimized, well-managed system, deep percolation and runoff can often be assumed to be negligible.
Because if you are managing your irrigation perfectly, you aren't flooding the field to the point of losing water to the deep earth or the nearest ditch. So that covers the soil holding the water. The next submodel is the atmosphere.
Right, the atmosphere. The sources list the inputs here as daily maximum and minimum temperatures, solar radiation, wind speed, rainfall, and relative humidity. But rather than just listing weather metrics, we should probably look at how these specific inputs actively pull the water out of our soil bank account.
Think of the atmosphere as a giant vacuum. Solar radiation provides the thermal energy required to vaporize the liquid water sitting inside the plant leaves. Then, temperature determines how much moisture the air can physically hold.
And what about the wind?
Wind speed acts as the physical force constantly stripping away the humid boundary layer of air sitting just above the crop canopy.
So if the wind doesn't blow that humid air away, the vacuum basically loses its suction.
Precisely. If the air around the leaf is fully saturated, the plant just can't transpire. The wind continuously replaces that saturated air with drier air, maintaining that atmospheric pull.
Okay, and then you add in the management submodel, which accounts for the human interventions, like when you irrigate, how much you fertilize, the specific farming practices altering the environment.
Right, all those daily human choices.
So we have built the virtual farm, we have set the daily clock ticking, but to make the simulation work, we actually have to put a plant inside it. And simulating a living organism day by day seems like an invitation to get bogged down in that impossible complexity we talked about earlier.
It does, which is where the model employs some incredibly elegant mathematical shortcuts. Let's look at how it handles the root system, for example.
The source notes that root development is expressed simply as rooting depth over time. And crucially, there's a functional relationship established between root development and shoot development. This implies the top and bottom of the plant are mathematically tethered together in the simulation.
Right. As the above-ground canopy grows and demands more water to fuel its expansion, the root system must dynamically push deeper into the soil bank to find the necessary moisture.
And the model calculates that expansion proportionally, rather than trying to map the chaotic fractal geometry of thousands of individual root hairs.
Exactly. It finds the functional outcome without simulating the microscopic chaos.
But the above-ground leafy part of the plant, the canopy, is where the model makes a choice that feels almost controversial. The lecture explicitly states that canopy development is expressed strictly as canopy cover of the ground. It specifically avoids using the more traditional leaf area index, and I really have to push back on this choice.
Oh, really? Why is that?
Well, if our ultimate goal is to know exactly how much a plant is transpiring, wouldn't it be far more accurate to measure the total surface area of every single leaf on that plant? That is what the leaf area index attempts to do, right? It maps the 3D geometry of the foliage. Why does AquaCrop actively ignore all of that data to just measure the two-dimensional shadow the plant casts on the ground?
Okay, imagine trying to computationally model the exact angle, the curvature, the overlapping shade, and the surface area of every single leaf in a massive 100-acre field of wheat, and then recalculating that geometry every single day as the plants grow and the wind blows.
Oh, wow. Yeah, that sounds like a computational nightmare.
It absolutely is. The margin for error when measuring that in the real world is massive. By measuring the shadow, the canopy cover, they take a hyper-complex 3D problem and reduce it to a clean 2D mathematical expression.
The source actually mentions it uses a simple S-curve, a sigmoid function, for that canopy growth.
Yes, it does. From a functional standpoint, the shadow tells you two critical things with profound accuracy. First, it tells you exactly how much sunlight the plant is catching to perform photosynthesis. And second, it tells you exactly how much bare dirt is being shaded, which dictates the drop in that wasted soil evaporation we discussed earlier.
Okay, that makes sense. It saves immense computational power while perfectly capturing the mechanics of energy capture and water use. That is an incredible workaround. And the source mentions a decline function for senescence, which is the biological aging and dying back of the canopy as the season ends. It also notes that the harvest index, that ratio of edible grain to raw plant matter, increases linearly with time starting right after pollination until near physiological maturity.
Right, because once the plant pollinates, its biological imperative shifts entirely. It stops devoting energy to building more green leaves to catch sunlight and instead pours all of its gathered resources into filling out the seeds to ensure the next generation. The model tracks that linear shift in energy allocation.
But nature rarely grows on a perfect mathematical S-curve. Things go wrong. We talked about acute trauma earlier. So how does this simulation account for the physical suffering of the plant when the soil bank account runs dry?
Through what the model calls stress coefficients. This is how water stress is simulated inside the plant's virtual biology.
The lecture notes that these coefficients act on specific basic growth expressions. They alter canopy expansion. They alter stomatal control of transpiration. The stomata being those microscopic pores on the leaves that open to release water vapor and take in carbon dioxide. If the plant is dying of thirst, I assume the model forces those stomata to slam shut.
It does, yeah. The plant sacrifices its ability to take in carbon, which essentially stops its growth, in order to hoard whatever water it has left inside its tissues. The stress coefficients also alter canopy senescence, forcing the plant to prematurely yellow and drop leaves to reduce its surface area and save water.
And the sources highlight that these coefficients can alter the final harvest index itself.
The true brilliance of using distinct stress coefficients is robustness. It accommodates the wildly different sensitivities that different crop species have to water stress.
What do you mean?
Well, a 2-week drought might trigger a survival mechanism in a drought-resistant crop like sorghum that temporarily halts canopy expansion, but leaves the final grain production relatively untouched.
Ah, okay.
But that exact same 2-week drought in a sensitive crop like maize might irreversibly damage the pollen, immediately devastating the harvest index. The daily simulation tracks how those unique species-specific stresses cascade through the plant's life cycle.
It is genuinely amazing how they have managed to capture the essence of a living, breathing thing inside these algorithms. Let's pull all of this together and distill the journey for you because we have covered a massive amount of ground today. The FAO spent 30 painstaking years building AquaCrop with a very distinct philosophy, perfectly balancing simplicity, robustness, and accuracy.
And they achieve that balance by refusing to get lost in biological trivia, choosing instead to, well, follow the water.
Exactly. They realized that measuring total water use was muddy and inaccurate, so they mathematically separated the wasted evaporation of bare soil from the highly productive transpiration of the crop. They moved the simulation away from annual estimations and put the plants on a rigorous daily health check within the soil-plant atmosphere continuum.
Tracking the daily deposits and withdrawals from the soil, the daily vacuum pull of the atmosphere, and the daily physiological trauma the plant endures.
And finally, they used elegant shortcuts, like tracking a 2D canopy shadow instead of a 3D leaf maze, just to reliably predict exactly how much biomass and edible yield a specific amount of water will generate.
It really is a triumph of practical engineering over theoretical bloat.
Which brings us to why this matters to you. Whether you are a policymaker tracking global food security, an engineer working on regional resource management, or just someone fascinated by how we mathematically decode the natural world, AquaCrop represents the ultimate tool. We are navigating a reality where every single drop of fresh water counts more than it did yesterday.
Oh, absolutely.
Having a reliable mathematical translation of how seeds turn water into food is quite literally a matter of global survival. It allows us to simulate the future and prepare, rather than just reacting blindly to whatever harvest the Earth gives us.
The ability to run climate scenarios and see the specific daily impacts on global food staples before the seeds are even planted is just invaluable.
But as with all deep dives into the mechanics of the natural world, solving one equation usually just reveals another shifting variable. I want to leave you with a lingering thought based on a very specific detail buried in the source material. We mentioned earlier that water productivity is normalized for climate, using that reference, atmospheric thirst. The source specifically notes that this normalization also inherently includes the atmospheric carbon dioxide concentration.
Right, because CO2 is not just a greenhouse gas in this context. It is the fundamental building block the plant is inhaling to construct that biomass.
Exactly. The baseline mathematical relationship between water transpired and biomass created assumes a certain level of carbon in the air. So here's the question to chew on long after today's deep dive ends. With global CO2 concentrations constantly shifting, how will our mathematical models have to continuously adapt?
That is the big question.
Right. If the very air the plants breathe is fundamentally changing the baseline efficiency of water productivity, how quickly can our math keep up to accurately predict whether the food webs of our future will thrive or wither away?
It guarantees that the simulation will never truly be finished, the environment never stops moving, so the mathematics can never stop evolving.
The waters just keep getting muddier, keep exploring, keep questioning, and we will see you on the next deep dive.